Hi, Jim. You're muted still. Good morning.
You hear me now?
I can.
Okay.
How are you?
I'm doing well. Yourself?
Good. I apologize for some of the background noise. They're mowing grass outside right now. So
Okay, it'll probably help my presentation.
no, believe me, when you start, I'm gonna mute myself and stop my video. You'll find that a lot of people will do that unless they're actually speaking. They'll just kind of hide. So don't be alarmed. We're all paying very close attention to you. So yes,
Well,
so Jim Smith is going to introduce you
oh, nice.
today. Yeah,
That's
yeah.
good. Good for
Well,
him.
hopefully he'll be joining us soon.
Nice.
How's your week been there?
Well, it's fine. Nothing new to report. I'm been madly reading books and stuff like that, and just kind of enjoying retirement.
Oh, good for you. Good for you. I'm jealous.
Oh, don't worry. It's better to be young than retired.
Oh, I'm not young, so.
Oh, come on. You're a lot younger than I am.
Oh, I don't know. I just had a visit this past weekend with my first grandchild.
Oh, that's exciting.
So, yeah, so it's very exciting.
Was that nearby where you live?
No, they live in Minnesota.
Oh, okay.
They live in Ely, Minnesota. My son is the head canoe master at Camp Widgiewagon in Ely,
Cool.
Minnesota. Yeah, he started out working at Outward Bound, going on canoe trips with troubled youth, and met a girl and decided 50 days out in the wilderness was just a little too much. So he's now working for the YMCA and is the head canoe master there. So
Cool. Did you get to go for a canoe ride?
a couple falls ago, yes, and
Oh, okay.
encountered a bear on one of our October trips. So it was quite interesting. But no, this past weekend I played grandma and they got out for one last boat ride. Just the two of them. So
Good. I see Jim Smith is online, though he's hiding himself. No video or anything.
Jim, don't hide.
Is the perspective okay?
Yeah, it's perfect.
Okay, good.
Mm-hmm. From Jim to everyone, and he's setting up his webcam.
Oh, I see. I see Chris just joined as well.
This is going to be joining us.
Hey.
Hi, Chris.
Hi, Chris.
How's everybody doing?
Well, thank you. Yourself?
Good, good.
I got a message when I logged onto my Linux laptop this morning. It said, "There's a new version of Zoom available. Do you want to upgrade?" And I said, "No, just leave it alone."
Oh no.
I'm with you, Jim. That scares me too.
It's actually gone remarkably smoothly, especially given that it's a Linux system, which tends to not get a lot of attention. But I have to give Zoom their credit. They've done a pretty good job, especially given the amount of pressure they're under these days.
Yeah. Which builder or which flavor of Linux are you using?
I'm running Fedora 32.
Ah, that's right. I remember now.
Yeah, I started using Fedora a long time ago, when it was like Fedora 6. And I just got used to it. I'm very familiar with the system administration, and I've used other variants of Linux as well, but I don't know, for some reason I've just stuck with this one. It's, as you mentioned, I think last time we chatted, it does tend to be a little cutting edge sometimes, which is sometimes good and sometimes not. Mm-hmm. But all in all, it's gotten ever more stable as the years go on, and I just like it.
Yeah, It's really nice. Like you can kind of beta test some of the new features that might pop up in REL,
Hmm.
but you don't have to pay what you would pay for REL satellite updates, everything like that.
Right. Um, would it be worth doing a test presentation, screen share at this point?
I would say so. Yeah, it might be good just to have get your screen share up and just keep it on the title slide for when people start to arrive.
Okay, let's see. Okay, well, this looks hopeful. Um,
I can see it.
okay, now I think I have to go to slideshow mode.
Oh, you know what though? Yeah, go ahead slideshow, but I think you might have to stop sharing and reshare.
Stop what?
So stop sharing your screen and then reshare it again, because we're still looking at the slideshow not in presentation view.
Oh, okay, so hold on just a second. So I don't leave the meeting.
Yeah, you want to go back to share screen, and then it should be the top left option, desktop 1, or if you have multiple screens, it might be like desktop 2.
Um, oh, I see, desktop 1. So do I want the desktop or do I want the presentation? Which of those should I share?
I would do the desktop, because what can happen sometimes is if you're sharing just the presentation app window, but then you
Uh-huh.
go into a different window, we don't necessarily see, like it might gray out the
Oh,
presentation.
okay, so let me start slideshow mode again and let me know if that helped.
That's perfect. We got a full screen now of your
There you
presentation.
go. Yeah, that
Okay,
looks
cool.
good. Mhm.
Yeah, I wouldn't have been able to tell that from here. It all looked perfectly fine.
Oh yeah, that's why we test this out beforehand.
Yeah.
Oh, it looks good. What's your weather look like out there, Jim?
Oh, it's very typical for this time of year. It's overcast. It's not raining. And hold on a second. I'll give you a temperature update. I'm guessing it's probably around the high 50s or something, but 54. um,
Okay.
Typical weather here right now. And I love it. I mean, we have a beautiful summer here, but I'm one of those people who doesn't mind overcast and rain and the kind of stuff that drives some people crazy.
Yeah, that's good. That's about the same weather we have here right now is some overcast days, 50 to 60.
Yeah.
It's sunny here where I am. I'm in Toledo, Ohio, so
Okay.
about an
Uh-oh. There's
hour and
Jim
a half
Smith.
south.
Do I have to put a mask on for this now that Jim Smith has entered?
I so I'll show you in a second. I'm out in our towing tank because my office space is back in kind of a shared space with students.
Uh-huh.
So in this tank, I'll show you in a second. I can close the doors. It's nice and big and open. And then rather than when I'm introducing you with a mask on and being muffled, I came out here. So
That makes sense.
but I was having trouble at first. I'm like, there's 2 or 3 different computers out here, and I didn't know which one to plug my my webcam into. So I'm glad I have it figured out. So
Yeah, you're obviously successful.
yes.
There's no hiding from the rest of us now.
Amber made me. She's like, okay, well, you have to have a collared shirt on. So
Oh, really? And I went out of my way to wear my Hawaiian shirt.
that's
That's
good.
what you can do when you're retired.
Absolutely. But yeah, I'm gonna be messing around with a cord right here real quick, but
Sure.
but yeah, Jim. So this is our towing tank. So down that direction is south. So that's the full you know, you can kind of almost see it down there. That's the full 100 meters or so down that direction.
Yeah.
And then this direction is north, and that grading down there, we call that the beach. So that's to help to dissipate waves. At the south end, there's a big stainless steel wedge style wave maker.
Okay.
That, you know, they can create waves with. But then, yeah, this is the carriage, we would call it. And then those two rails right there, there's that component in the center. That's where we hang stuff when we're dragging it through the tank. So
Okay.
where we, you know, in models, like you can see some of the models, you know, that are up on those racks over there. Some of those are used for ongoing tests for labs and stuff. So there's actually a rowing hull that a student was doing some testing on in the fall, right before all the COVID stuff went down. So.
Oh, okay. Jim, I did see a YouTube of you. You never showed your face, of course. It was you were in stealth mode, but it was kind of fast action with you and some CNC machine zipping along. I don't know, it was a milling machine or something like that.
Yeah.
Just so you know, I'm watching to make sure you're working.
Again, because of you know, COVID and whatnot right now, and we don't have the ability to do large student tours for, you know, undergrads or undecided, you know, freshmen and sophomores. We're trying to get more, you know, content online. So, and that was for for an upcoming project.
That makes good sense. So will anybody listening in on this seminar actually be in a room together, or is everybody kind of linking in by their own Zoom accounts?
Jim, as far as I know, the students will not be joining together in groups. I mean, they may be if they can find some place to social distance, but we had talked about trying to allow them to come into one of our rooms at one point, but decided it wasn't a great idea.
Yeah, it's just too hard these days.
It's just hard. You know, we're missing the community of everybody getting together. I mean, typically these events were held around luncheon, and we packed the students in a room with the presenter, and it was great. So yeah, right now we're doing what we can to try to keep community and keep students engaged. So
yeah, well, yeah, I mean, it's just a hard time for everybody, and I don't know. I'm optimistic that if the science/medical community is given an opportunity to proceed at the same pace that they usually do, I think we'll get through this with some time, but it's not going to be fast.
Right.
I think that's just the reality of it.
Hi, Leslie. Hi, Jim. It's Jean.
Hi, Jean. How are you?
I'm good. Thank you. Yeah, I just want to stop by, say thank you. And I was actually looking forward to this talk, but I got drawn to another meeting at 1 o'clock. But I want to stop by. This is actually, seeing another I noticed you are electrical engineer. Your background is electrical engineering. So I'm the lonely electrical engineer in this department. So I figured that I would stop by and.
Well, I appreciate that. And yeah, I actually looked up your web page just because I like to kind of know who I might be interacting with, and I noticed your background in control theory and such. We've had some similar educational experiences, I guess.
Yeah. So where are you now, physically?
Well, I'm sitting at home. I retired last October. I still do a little bit of work once in a while, but not a lot. So yeah, I'm just sitting in my living room. My gas fireplace is glowing away. You can't see it right now, but it's keeping me warm and my cat warm.
That's good. I was wondering if you are in Hawaii or
Yeah,
on that
I was
boat.
joking that that's what you get to do in retirement is wear Hawaiian shirts.
Yeah. Nice.
How long
Yeah.
have you been department head, Professor Sun?
Oh, this is my 4th year.
Okay.
I joined the department 2003, so I have been here for about 17 years.
Oh, okay. Did you come right to Michigan following your work in Southern California?
Well, I came to Michigan, but I moved in Michigan in a number of places. So my first stop was actually Wayne State in the electrical engineering department.
Oh, okay.
Yeah, then I went to work for industry for about 10 years before I come back to academia. So I have been in Michigan. I worked at Ford for 10 years
Oh,
for powertrain control.
I think it's nice to have folks in academia who have had experience in industry. It brings a perspective that you oftentimes don't get in academia.
Well, that's my perspective, but I could be biased, and it worked out for me. I think that experience served me well. So yeah. Well, I had a former student joined John Hopkins applied physics lab about 2 or 3 years ago.
Okay. Yeah,
Yeah.
they're much bigger than the applied physics laboratory where I worked and where Jim Smith worked. I mean, I've always made the claim that there's like an inverse R squared spreading law. The closer you are to Washington, D.C., the more money you get, and hence the larger you are. And they're about 20 miles away. So.
Yeah. So I didn't know that you and Jim had the pre-existing condition.
Yeah. Yeah. We it was fortunate for me that we were able to hire Jim into our group, and we worked very closely together for, I don't know, as long as how long were you at the lab, Jim? Like 5 years before you decided to head back home to Michigan?
It was more like 7.
7,
but
okay.
you and I closely working together, I think was, about 5 or 6 of that. So, you had to go and retire, and I think that there was a cascading effect with several people that ended up leaving the Seattle area afterwards. That tends to happen, I think with good faculty and, and good principal investigators but no, yeah, seriously, it was great out there, but yeah, Michigan is home for Amber and I, so.
Yeah, I understand that, and I can certainly appreciate the allure of getting back to your home state, and you're nearer to your family and all that. So
yeah.
Well, I don't want to. I see we're kind of at 10:45 plus. Should we get going on the seminar? I know people have schedules back there, unlike me.
So Jim, before I just want to say thank you. And if I sign off after 15 minutes, you just excuse me for, I will watch the video afterward.
Oh, well, I understand completely. So you're too important. That's why you're in meetings all the time.
We are not doing important things. That's why we were asked to go to meetings.
Indeed.
People like Jim Smith, they are doing important things.
I understand that perspective. Well, thank you very much for taking the time to join, and don't worry at all about cutting out when you need to.
Thank you.
Take care.
So I guess I'll introduce you now, Jim. And I know I promised that I would only call you Dr. Luby once. So I'll get that out of the way right now. I worked with Jim for 7 years. Maybe some of you overheard when we were talking to Jing. I worked with Jim for 7 years at the Applied Physics Lab. It doesn't seem like that long ago that we were out on the Jack Robertson in Puget Sound, putting together the delivery of those last few Carina gliders, so the one you're standing with right there. And yeah, it doesn't seem, like that long ago that we were doing that. And, to work with undersea vehicles kind of takes a certain mindset, because they can disappear for hours and hours. And, once you lose acoustic track of them, you just hope they come back and they call back in and, let you know that things were okay, and they download their data. So, I can recall plenty of times kind of with crossed fingers, hoping that I torqued all the bolts correctly, and, all the thousands of lines of code are doing what they're supposed to, so the gliders come back. And those were a lot of the times that I think the information that Jim is going to talk about today, those were, when we were waiting, those were a lot of the times that, Jim was a good mentor and teacher, kind of teaching me the things that he's going to go over right now. And I'm glad that, Jim's here today. Underwater vehicles, and especially gliders, they're a smaller known type of technology. So for Jim to be able to, hopefully, bring up some questions in young engineers' minds, and, inspire the next generation. That's, certainly what he did with, with me and, our colleagues at the University of Washington. So without further ado, it's my privilege to introduce Jim Luby for today's project speaker.
Thanks for the kind words, Jim. Well, I can't really tell how many other people are out there. I see a couple of little windows, but I assume that's by design. But welcome to everybody else who happens to be listening in. Again, I'm Jim Luby, that guy standing in front of that glider that we named Carina. And I'll be showing some more detail on that later in the presentation. So I will move forward and just see here. So, I'll have, one slide, the next one, just a little bit of my background. Then I'm going to try to provide a historical overview of the development of undersea gliders. It's all happened over the last 20 or so years. I'll talk about principles of operation, and then kind of show the first generation. There's kind of 3 first generation gliders that were developed. And then a project that I was involved with colleagues at the University of California, San Diego Scripps, on a flying wing glider, which is kind of interesting. And then I'll describe the Carina glider development effort that Jim Smith and I worked closely on together for 5 or so years. And then I'll finally discuss an application, a use of gliders to do some marine mammal monitoring. So my background, I'm an electrical engineering product of, public universities in America, much like the great University of Michigan. So I have a, bachelor's and EE or electrical engineering from University of Connecticut, a master's in Colorado State and from Colorado State, and then a PhD that I attained at the University of Washington while I was working at the Applied Physics Lab. I did get a couple of years off with a fellowship to finish my PhD, which was a fellowship provided by the lab, which was very nice. When I finished my master's degree at Colorado State, I took a job at Boeing Aerospace up here in the north, just south of Seattle. And I only stayed there 1 year because I got an offer from the Applied Physics Laboratory. But while I was at Boeing Aerospace Corporation, I worked on spacecraft guidance systems, and I learned a lot, actually. So even though it was a short time, it was very interesting to kind of learn that technology. But then, starting in 1979 and for 40 years afterwards, I was at the Applied Physics Lab, University of Washington. I may refer to it as APL throughout the rest of the talk. And, I've kind of my skill set, if you will, is, especially when I was an undergraduate, I kind of had a focus on automatic control systems. And then when I went to Colorado State, kind of switched gears and got into digital signal processing, which at that time was kind of a nascent field. Nowadays, everybody's doing it and it's all over the place. But then it was not so. And in particular, that's how I ended up at the Applied Physics Laboratory. They were looking for someone with kind of recent graduate experience in digital signal processing. And so they found my name through a chain of other folks and made an offer to me. And I went there. And since going to the Applied Physics Lab, the focus of the Applied Physics Lab is underwater systems in general and a lot of underwater acoustics. So I worked on statistical signal and array processing, underwater acoustics, real-time sonar simulation. And then in the last, 8 to 10 years of my career is when I started working on undersea gliders, which was a whole new thing for me. Not something you tend to take courses in as an electrical engineer. So let me start just giving the overview of undersea glider development. It was really, the development was motivated by the very high expense associated with getting oceanographic data. Typically in the old days, 20, 30 years ago, and prior to that, oceanographers would go out maybe once a year, maybe twice if they were lucky, on large research ships, and go to various latitude, longitudes, and drop stuff in the water, lower it down to various depths. So it's definitely a three-dimensional sampling problem. But the cost of those ships is really high. I mean, even back 30 years ago, the cost of an oceanographic research ship was probably something like $30,000 a day. And that's just for the ship and the crew. That didn't include any of the scientists or engineers or any of the gear that they brought along. So it really limited the amount of data that could be collected. So kind of in the mid-90s, the Office of Naval Research, ONR, decided, well, with the technology that's come along in computers and low power electronics and such, maybe we can develop these robotic ocean sampling systems that can replace or at least supplement some of these very expensive research ship cruises. So ONR, under the auspices of Dr. Tom Curtin, funded 3 development programs simultaneously. One was ended up with a glider that I'll show these 3 gliders on the next slide, but University of Washington Sea Glider, and then one at the University of California, a glider called Spray, and then a company in Massachusetts, Webb Research, that developed a glidem called Slocum. And let's see, and then again, this is kind of just a high level. I'll be talking about these things in a little more detail in subsequent slides. But around 2004, ONR decided to, funded a collaborative effort between where I was at APL, University of Washington, and folks at Scripps in San Diego to develop a flying wing glider, which was a kind of a short-lived project for me, but it was very interesting. And I'll show some pictures from that later on. And then more recently, well, kind of recently, I guess, 2008, the ONR again, based on the positive results that they had seen with the first generation gliders, funded us at APLUW, University of Washington, to develop a new glider with a focus really for the Navy, not for the scientific community, but more something that could be used by the Navy. So I just list a Wikipedia reference at the bottom. If anybody's interested, they can get more detail on this historical stuff. So these are the 3 gliders that resulted from that initial round of funding from ONR. They're all about the same size, weight, and all that. They look different, but all of them have been successful. Initially, the Slocum, the one at the top, was developed as a shallow water glider. It was designed to go down to 200 meters. The Spray glider from Scripps, I believe, is a 1,500 meter rated. And then the Sea glider, which was developed as a collaboration between the Applied Physics Lab at the University of Washington and the School of Oceanography, is rated for 1,000 meters. So anyway, I'm going to keep moving along here. So I want to kind of describe kind of what does it mean? What is a basic glider doing? Well, imagine, you know, a couple of those small gliders, like the sea glider I showed on the previous page, are put into a small boat, kind of a, you know, fishing boat or even a large rib boat. And someone, you know, a team of two people typically, you know, would take them, you know, and bring them out to a launch point, basically where the water was deep enough, and place them overboard. And as soon as they put them overboard, as long as we did our ballasting correctly, they would float and they'd be pitched nose down and stick an antenna up out of the water. And that antenna would have two functions. One, it could get GPS, so the glider immediately knew where it was. And then it also had an Iridium satellite antenna and a radio system inboard so that it could relay the GPS coordinates up to a base station, which, you know, oftentimes would be back at our lab, but in general could be located anywhere in the world with internet access. I actually spent quite a bit of time controlling gliders from home, sitting on my couch on a weekend. You know, so it really didn't really matter where the base station was. You could log into it and keep an eye on the gliders. But imagine, you know, the gliders, you know, sitting on the surface, and basically once it's in the water, the folks out on the boat can just kind of stand back, and because it's all, you know, the control of it has been turned over to the remote operator wherever they're located. And once everything looked good in terms of kind of the basic health data coming up over the Iridium link, we would give it a go command essentially, and it would make itself negatively buoyant. And I'll describe that in more detail in subsequent slides. And, you know, pitch to a certain angle, and then it would start a dive along a trajectory. I'm hoping that you'll be able to see this pointer. I don't really know how well that'll work, but anyway, you know, the glider would make itself negatively buoyant and then glide down to some predetermined depth where it would basically pitch up and make itself positively buoyant and then ascend to the surface again on another glide path. When it got to the top, it would pitch over so it exposed its antennae, and then, you know, start talking to the base station again. Now, typically we'd have the, you know, the field crew hang around for one or two shallow dives, by which I mean, you know, 50, 100 meter depth dives. But if everything looked good, we'd basically release them to go back to land. And then from that point on, everything was under remote control from the workstation. And then we'd start sending the gliders on deeper dives typically. And then once they're going, it just does this cycle over and over and again. And in fact, you know, it wasn't necessary for us as so-called glider pilots to be looking at the base station when these things logged in. We had it set up so they were quite autonomous. They would call in and if they would check for some files. You know, we could put in new waypoints and dive depths and such if we wanted to. But if we didn't, they would just check in, send us some status data, and then go on the next dive and just keep going. So it's a very autonomous system. Let me move forward. So, you know, everybody's probably familiar with, you know, the typical propeller-driven vehicles, which tend to go down to kind of some depth, turn on, you know, their propeller, and then they go from point A to point B, pretty much staying at the same depth. Gliders don't do that. They basically take these zigzag patterns, such as I showed in the previous slide, which are sometimes referred to by people as yo-yos. But if you think about it, you know, a glider or any vehicle has a density. And of course, the water has a density, which typically varies with depth because of salinity and temperature and other things. But if the glider makes itself less dense than the surrounding water, effectively it becomes relatively heavy. It wants to descend. Or if it makes itself, well, I think I said that backward, but you know, the next two bullets basically say what I'm trying to say. The glider is essentially changing its buoyancy to either go down or go up. And it can do that by changing mass, or its volume, or both. Submarines, you know, oftentimes they tend to take on water and pump it in and out of large tanks. And they're not changing their volume, they're changing their mass. The gliders have tended to do the other, that namely use a variable volume approach. And I'll show an example of that again in a moment. then the last point I'll make on this slide is that, both weight and buoyancy are gravitational forces. And so if you want to move laterally across the ground, over Earth, one way or another, you've got to transform some of that vertically oriented buoyancy force to forward motion. And that's done in gliders by having wings and adjusting the pitch of the glider so some of the force is transformed to lateral. Now this is the kind of slide that everybody, this is for the younger people here, that it's just loaded with lots of details, and this kind of slide they tell you shouldn't present. So I'm not going to spend a lot of time on it. I wanted to throw it into the presentation so that if folks got a copy of this later, they could kind of look at some of the equations that govern, weight, displacement, density, and buoyancy and such. But again, I'm not going to talk about it. I kind of covered it, semantically in my description on the last slide. So here's a view of the Sea Glider. This is the one from the University of Washington. And at the top, this is painted in lovely pink, is the fiberglass fairing for the glider, and it comes apart at this seam right in front of the wings. The greenish sections here are the anodized aluminum pressure hulls that are rated to, well, routinely the gliders go to 1,000 meters. These are rated higher, maybe 1.5 times that. At the bottom is the antenna. The antenna is actually out on the tip here, but it's on about a little less than 1 meter long fiberglass shaft, just so that when the glider comes to the surface, it gets the antenna far enough up out of the water. Internally, this is a primary lithium battery right here, and it moves fore and aft on a screw drive. And by doing that, you can adjust the pitch of the glider, move it forward, the glider pitches nose down, move it back, nose up. Can't really see it in this picture, but this battery pack also rotates left and right, or port and starboard, if you will. And that allows the glider to bank and make turns. So there's no actually external moving parts on this particular glider. I'll show you examples of others that do have some moving parts later, but it's kind of a cool thing that it's all, there are no external parts, and it can fly perfectly well with just this mass shifting of internal components. The key maybe to the whole concept of gliders is back here, the variable buoyancy system. There's a reservoir here inside the pressure hull that holds 800 cc's of hydraulic oil, basically. And then there's this flexible bladder or bag hanging out of the back of the pressure hull that would be up inside this water-filled housing back here. And you can, if you imagine that all the oil starts out inside, well, that means the glider has minimum volume. But if you pump all that oil out and expand this bladder on the outside, that effectively increases the volume of the glider by 800 cc's. It doesn't change the mass. The mass of the oil is just moving from inside to outside or back. And so, but it does change the density. So again, by controlling the density of the glider with respect to the density of the water, you can make it go up and down. So when a glider is flying, the vast majority of time when it's underwater, it's in what we refer to as steady state or unaccelerated flight. Certainly it does experience accelerations when it's leaving the surface or when it's turning around at the bottom of a dive and coming back up, but those are relatively short fractions of time compared to the overall duration of the dive. So most of the time these equations apply, and there basically are three forces that play here. If you think the glider is moving along this slope here, which I'll refer to as the glide slope, and it's got a pitch angle that's measured with respect to horizontal, and then it's got an angle of attack alpha, which is essentially the angle that the water is flowing over the vehicle. So there's the drag force, which is defined as opposite direction as the glider is moving along the glide slope. And then the lift is defined orthogonally to that and pointed up here. And then finally, there's this net buoyancy term. And, the third equation down here, the net buoyancy is just the difference between buoyancy and weight. And if it's, you can make it positive or negative depending on whether you want the glider to ascend or descend. Well, if you look at this, if you work through this geometry up here and the force, there's got to be a force balance because those three forces, L, D, and delta B have to sum to zero in steady state. So what it comes out to be is that the net buoyancy times the sine of the glide slope has to equal the drag force, and the net buoyancy times the cosine of the glide slope has to equal the lift. And if you divide, this equation by this one, sine over cosine is tangent. So you get this relationship that shows that the glide slope is determined by basically the drag over lift ratio. Usually people will talk about lift to drag ratios, which is why I chose the semantics I did there. But you can see the equation. The tangent of the glide slope is D over L. So, it's kind of interesting, the speed of the glider kind of, it's inherent in the D and the L, but it's a very simple expression. So again, the majority of time, the glider is flying in this configuration and it's very stable. And that has some advantages, which I'll talk about shortly. In particular, I guess on this slide, I just want to say at the beginning that gliders are not perpetual motion devices. They just use energy in a different fashion than people are used to. And I've had many people, they say, ask, and smart people say, well, if you put this glider in the water and you make it negatively buoyant and it starts going down, can't you put a propeller at the back of it so the propeller spins and runs a generator and recharges the battery? Well, yes, you can do that once on the way down, but when it comes time to come back up, you pay the price for that. I'm not going to go into a lot of the details on that right now, but suffice to say, like any other thing, any other vehicle, gliders require energy and they're pulling it out of their battery packs. Now, the way most of these undersea gliders have worked is, again, changing their volume so as to change their density. And when it's at the surface and it's time to start a descent, it sometimes we'll use a low pressure pump to reduce the volume of the glider by moving oil from the external bladder to the internal bladder. But you can also just rely on hydrostatic pressure and a bleed system, open a bleed valve essentially, and let the oil move in. And it takes longer, but at some point, as you get a little bit deeper, it starts flowing faster and faster. And you can reduce the volume without actually using any energy pretty much at the surface. Where you really pay for it is when it's time to come back up. You get to the bottom of a dive, which we refer to as the dive apogee. Then you have to run your pump to increase the volume, and you're doing that against high pressure. The pressure at 1,000 meters, which kind of the deepest our gliders at least are designed to go, is roughly 1,750 pounds per square inch. Excuse me. So, and the mechanical work that's done in pumping is the product of how much volume you change. In other words, you need to make the vehicle's volume grow so that it becomes positively buoyant and go back to the surface. So it's the product of that volume change times the pressure, and it's divided by the efficiency. And efficiencies in these systems are typically 40%. You're lucky if you can get them to 50. But anyway, and the work is force times distance, and because most of the time the glider is in steady state, the speed is constant, the drag is pretty constant. So really, if you look at that, power is the time rate of change of work, and because drag is effectively constant, it doesn't have a time dependence. So it really, the DDT just is the time derivative of distance, which is speed. But we already know from the previous slide that drag is proportional to speed squared. So now we show that the power consumption is proportional to speed cubed. So as an example, if you wanted a vehicle that went twice the speed, it needs 8 times the power. And you know, these are really important, real basic kind of physics things to understand. You want to, I guess I say, the second bullet from the bottom, use the lowest speed you can get away with that's consistent with your mission objectives and other constraints. And so, for instance, a mission objective might be, I need this glider to get from point A to point B in a week. So, you know, that tells you right offhand, it's got to go fast, certain speed to at least meet that objective. But, you know, then there's always currents in the ocean, and it seems like Murphy's law that they're always pointing against you. That's not really the case, but you know, we try to look at current maps and estimate, you know, what the effect is going to be. You've got to plan all these things to use gliders effectively. But you know, I think the bottom line is we have figured out how to do that. And then one of the other things that is really nice, because the steady state glide is so stable, you can just put flight computers to sleep. You don't need, you know, closed loop control systems carefully monitoring things, because the basic physics keeps the glider on a very stable trajectory. So you can actually save quite a bit of energy by putting, you know, flight computers to sleep and just setting timers so that they wake up, you know, periodically and check depth and heading and make corrections if need be. I've kind of described, I think, what is on this slide. Again, you know, propeller-driven vehicles, you know, if you have a mission that, you know, it makes sense to fly at a constant depth, for instance, you don't need to change depth for sampling purposes or something like that. You know, propeller-driven vehicles are probably the most efficient way to do that. They do typically require closed-loop control systems to keep monitoring, you know, rudders and elevators and propeller speed and that kind of thing. But, you know, they can be made very efficient too. Undersea gliders, on the other hand, you know, if you want to move laterally across the earth, they've got to go up and down. And let's see, I talked about the other things. But as the bottom bullet says, you know, they're very well suited for missions where you want to sample things vertically, like properties of the ocean. That's why, you know, the oceanographers use these, or both, you know, oceanographers as well as the Navy. You know, they'll sometimes install sensors on the bottom and want to be able to communicate with them. And gliders are really nice for that, because they can leave the surface, get down deep, communicate with some system sitting on the bottom, grab some data from that system, and then come back up and relay that data back to land over the satellite link. So they can be used, you know, anyway, they're effective for that kind of a mission as well. So, you know, people oftentimes ask me, well, you know, are gliders better than propeller-driven vehicles? And I just say no, they're just different and they're complementary. You know, different missions suggest different approaches. So I'm going to, as I mentioned earlier, we namely APL, University of Washington, in collaboration with Scripps Marine Physical Laboratory in San Diego, were funded by the Office of Naval Research, Dr. Tom Sween, to look into the feasibility of a high lift to drag ratio glider. This was a real fun project. You know, because of those steady state equations I showed earlier, with, you know, the tangent of the glide slope is related to the lift drag ratio. Basically, if you have a high lift to drag ratio, it basically means you can fly shallow glide slopes. And for a given energy expense, you know, when you're pumping at apogee, you can go a long horizontal distance for a given expenditure of energy. There are other advantages, you know, having a larger area, if you will, on the vehicle, like the wingspan, allows you to do things like put acoustic sensing arrays and such. On a, you might say, a detrimental side, launch and recovery of these things is challenging. And so you can see why probably when you'll see something like this. And this was the first of 2 gliders that we built in that program. This is the X-ray glider. It's about a 20-foot wingspan or so. And you can see from this picture that we had to build a really, well, you might say pretty complicated launch and recovery mechanism. So the glider would typically ride out to the launch point on this this thing in the foreground of the picture. It was just bolted down so it could ride, stand the waves and such on the way out. When it was time to launch, a crane would lift it and plop it down in this net, and then this net would move back kind of like on railroad tracks and basically push all the way to the back here. And though they're hard to see, there's a vertical cable here and another one here that connect to the A-frame of the ship. So when the A-frame moves out, backwards out, the back of this apparatus rotated on a hinge here and here, and basically the glider would just float off. Now getting it back was a little more challenging because you had to find a way to grab a wingtip and then get it aligned. So, basically you do the other thing, you do the backwards operation. You get the glider up onto the net when the net's still down in the water, and then the A-frame of the ship would move forward and pull the glider up out of the water and move it forward and stow it back on its carrying frame, if you will. We built a second generation of this called Z-Ray. I'm not going to go into a lot of the details, but a lot of lessons were learned on the building of X-Ray that resulted in changes to Z-Ray. Again, it used the same launch and recovery system, but the lift to drag ratio for Z-Ray was about 11, which allowed it to do, to fly glide slopes as shallow as 5 degrees, and got it to go 2 meters per second through the water, about 4 knots. So it was a fun program and a little bit different. Okay, now I'm going to switch gears to the Carina glider, which was the one on the slide, the very front, cover slide. And the one that Jim Smith and I spent so much time working together on. The Navy certainly noticed that, the success of the smaller research gliders, if you will, in particular, the persistence, some of the small gliders like the UW Sea Glider can do missions for 12 months. That's, that's unattended. So you throw it in the water and go pick it up somewhere 12 months later. So that got their attention. But it also got their attention that, in particular, again, a sea glider that we were flying out in the Pacific Ocean, a typhoon came through, a big one, and it caused all the ships to basically run, get back to port or get to some safe area. The glider couldn't, they're pretty slow, so it couldn't get out of there, but it just kept happily coming up and reporting in, and right through the middle of the typhoon, it just kept reporting happily and sending up oceanographic data. So that got their attention as well. And of course, the Navy and the military in general are all looking forward to use of more robotic systems for both cost savings and to keep humans safe. So we were funded again by the Office of Naval Research in 2008, and this was again Dr. Tom Curtin, to build a glider that was a bit faster, a little bit bigger, and could host Navy systems, many of which they weren't sure what they were going to be. So we kind of had to build, leave some spare electronic slots and such, so when someone came along in the future, they would have somewhere they could plug a little electronic board into, and attach sensors on the outside and such. But here's a cutaway view of the Carina glider. And it's hard to see here, but the hull is, the pressure hull is in 4 sections. But up here in the nose, this is free flooded. And so for instance, this would be a place where we'd have an acoustic sensor that we could use for echolocation from a ship, or we have an acoustic modem so it could communicate, excuse me, with other vehicles while it's underwater, or with perhaps a platform sitting on the bottom, exchange data with it. In here, this is the battery pack. It's considerably bigger than the one in the Sea Glider, but same kind of principle. It moves fore and aft on a screw drive, and that's how you pitch the vehicle. Moving further aft, this is an electronics section that has 6 slots in it, 3 long ones and 3 short kind of half slots. We use the top 2 slots, 2 of the long ones for like the flight computer and the various other electronic systems, GPS, Iridium, and other things. But that left 4 slots that are available for future expansion for whatever kind of payload the Navy is interested in putting in this thing. The variable buoyancy system here is 4 times the volume of the one in Sea Glider, which leads to a doubling of speed essentially. But unlike the bladder that you saw with the Sea Glider earlier, it was kind of shaped like a punching bag. This one is an accordion bladder, and there's a comparably sized one in this grayish thing out here, which is in the free flooded area of the aft portion of the fairing. So again, just like with the other glider, you can pump oil from inside to out to increase the volume of the glider, or move it from outside in to decrease the glider and the volume of the glider, and that's what made it go down or up. We elected to use a rudder on this one because we believed, and indeed we proved in operation, that it would allow for faster, higher heading rate. We could turn more quickly than you can by just banking the wings. So here are some pictures, some specs for the glider. You can read the specs. I will point out that in the lower left photo, this guy who's looking backwards, that's your very own Jim Smith of the MHD facility. I think he's laying hands on the glider to asking it to behave before we throw it in the water. This picture and the one to the right of it are both shots taken out on Puget Sound. Fortunately, you know, having a really deep body of water so close by. I mean, this is Seattle right here in the background. We could go out, I don't know, half a mile and maybe, and get into 200 meters of water for testing. So, you know, it's over 600 feet deep. So it's very convenient. And then up in the top is one of 3 laboratory spaces that Jim Smith ran. And so we ended up building, I think, right around 15 of these gliders over the duration of the program, most of which are now at Navy facilities around the country. And but you know, they were all built at our lab. Jim led that whole effort. He built some of the initial ones himself pretty much, but then as we needed to build more of them, we brought other people in, and then Jim, fortunately or unfortunately from his perspective, had to assume somewhat of a managerial role at that point. Did a great job. So I guess the last part of my talk, I wanted to switch gears and talk about something, you know, an application you could do with gliders. So I'm going to talk about using sea gliders in particular to do marine mammal monitoring. So the Navy has test ranges, you know, around the world and generally, but certainly around the U.S. And you know, they test all their systems there, and including things like high power sonar systems. Well, there's been problems that have occurred in the past where there's been indications that certain species of whales are injured when these very high power sonars go off. So that's certainly not good for the whale, and and the Navy doesn't want to be causing harm to animals. So they funded us, again through the Office of Naval Research, to develop a system whereby we could, basically deploy one or more gliders on one of their test ranges. And, if you imagine maybe they want to do a 2-week mission, we could throw a glider in, it could monitor the area for a week, it would stay there while they do their mission for a couple of weeks, and then we'd keep the glider there for a 4th week, leading to a total of 30 days. And they wanted us to record acoustic data continuously for that whole period, as well as do automatic detection, in particular looking for the species called Cuvier's beaked whales. I will, just as an aside, these beaked whales are the most amazing animals. you know, I just read, I think last night online that there's a new record. I think they're considered the deepest diving marine mammals or whales. I think one was recorded to go to a depth of, I think it was 3,400 meters. And, you know, they take a breath. I mean, they have lungs like us essentially, and they take a big breath at the surface and dive down over, you know, that's over 10,000 feet deep. And they're down for almost 4 hours. It's remarkable. Now, interesting, they use sonar as well to hunt for, you know, food, prey. They like fish and squid in particular, I guess. And so I don't have a picture of this, but there's evidence from, you know, marine mammal scientists that have done research over the years that suggests that as the beaked whales, you know, leave the surface and start descending, they fly kind of helical trajectories going down. And then they use active sonar pings, essentially like, imagine a spotlight going off, like radar almost. It's like ping, 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 ping. The whole time they're slowly circling down, and they're using that active sonar to find squid and other good things to eat. So that meant that there was an opportunity for a glider with the proper acoustic system and sensor to be able to listen and pick up on those. So we built such a system, you know, put it into we built a recorder detector board and integrated into several gliders, and then conducted missions at 3 different Navy test ranges. You can read the specs down in the lower left of the board we built, but as will become more evident in the next slide, I mean, these animals, you know, the human range of hearing is at best, if you're young, you know, we can hear up to maybe 20,000 hertz or 20 kilohertz. These whales vocalize starting at a low of about 15 kilohertz and going up almost to 80 kilohertz. So it's very wideband data, which necessitates a high sampling rate. So we built this system to take data, 16-bit samples at 250,000 samples per second for an entire month and store it on solid state cards. So let's see. On the left of this figure are kind of at the beginning of the program, we were giving these plots that, you know, marine mammal scientists had published in the past, and said, well, here's what you're looking for. They were kind of helping, you know, tell us, here's what you need to, you know, design your acoustic system to look for. So the plot at the upper left is the inner click interval. If you look to the right, you see these vertical lines that are about every 0.4 seconds. And over here, it's a little hard to read, but this probability distribution of click intervals is centered on 0.4 seconds. So they're as they're spiraling down or up, very, you know, almost right on the nose. Every 0.4 seconds, they're pinging, looking for something to eat. If you zoom in on one of these clicks, then you would get this image like on the second one down on the lower left. The one below that, it's a little bit hard to read, but it's essentially a frequency versus time plot. And then the one on the bottom is what's referred to as a power spectral density. And again, it shows the spectral content of their sonar, the whale sonar emissions. Again, you can see that starting at maybe 15 kilohertz, they have spectral energy that goes all the way up to at least 80, if not beyond. And what was remarkable, I think, for us is the very first time we deployed a glider-based system in an area where there were known to be beaked whales, we got this data on the right. And I mean, it was just remarkable to be looking through the data and then find these series of clicks like this and find, oh yeah, they're separated by 0.4 seconds, and zoom in on one. And if you look at the similarity between, this is a real click that we measured on a glider, it's almost a perfect copy of this one that we were given as a kind of a template at the beginning. And likewise, the power spectrum of this click very closely matches this. So it was really pretty amazing, actually. And it was really rewarding, I guess, to know that, you know, we had built a system that came back with nice, clean acoustic data that so well matched the species that we were looking for. So I think I've got 3 more slides, and I'm just going to kind of show you some of the trajectories, if you will, that we ran. So one of the Navy ranges that we worked at is called the Hawaii Range Complex. And this was, let's see, back in 2014. Like for instance, you see a D001, that's dive 1. So you imagine a small boat with a couple of our folks in it. Maybe Jim Smith was on these. I can't remember. Would go out here and dump a glider in the water here, and we would start to fly. And you can see these dive numbers incrementing: dive 1, dive 10, 20, 30, 40, and so. But because we were told in this case that there was evidence from the marine mammal community that these beaked whales like to hang around seamounts. So we specifically put a set of waypoints together to force the glider, or to have the glider fly around this path and essentially visit various seamounts. To save energy, with these red dots on the way out to this point, we kept the acoustic system turned off, just let the glider fly out. And we turned the system on, it flew this yellow trajectory, came back to this same point, we turned the acoustic system off, and then flew it back to a point where, I don't remember exactly how many days this was, but 230 dives later, the dates are in here, but I'm going to guess it's close to a month. Then, our folks could, fly back over to Hawaii and rent the little boat again and go out and pick up the glider and recover it and bring it home, and we'd get access to the data. Here's the Navy has a range in southern Alaska. You can see in this inset down in the bottom here, it's to the south of Alaska here. In this case, the marine mammal community had told us that, well, the beaked whales seem to like to hang out at the shelf break, where it goes from shallow water, this light bluish green, if you will, to very deep water out here. So we arranged for the glider to fly, from the, from this upper point. We went out with a small boat, threw a glider in the water. I think there were actually 2, I'm only showing one of them, and had it fly this zigzag trajectory to the southwest, and finally brought it back up. And on dive 200, we turned the recorder off, and we just flew the glider back and forth until the weather was convenient that we could send another small boat out to go recover the glider. And then we did 2 operations out on, it's called the Mariana Islands Range Complex the Navy uses. Navy has a big base on Guam, including submarine base, and they were interested in, finding out, or kind of getting a sense for what the population of beaked whales were on this range complex, which is very big. So in, I guess this one on the left is a 2014, and we sent a glider, basically launched it up here just to the west of Guam, and the Navy basically, we would have just come south, but I don't know if it was due to submarine activity or whatever. They asked us to go up and around to the north. So that's one of the nice things with gliders. You can just program in a set of waypoints and they'll follow them. So we had the glider fly up here, over here, turn the acoustic recording system on, and then, flew over to various points where the marine mammal community had suggested we might observe beaked whales. And then, at the end, we sent a boat out again, picked up the glider, brought it back, and had access to the data. This was about a 1-month mission, as I recall. Then again in 2015, we went out in here with 2 gliders. Very similar idea. We launched both gliders at the same point and sent one south and one north, just surveying again the 2 different areas. They flew for about a month, and we flew them back to a pickup point where they call in the GPS, and we just tell them, we send a small boat with our folks out on it, and then tell the gliders just sit on the surface and stop diving. And then, because they're sending GPS back to us all the time, we could relay that out to our recovery crew over an Iridium satellite phone. And they could go right to the point where the glider is, pick it up, recover it, grab the other one and come back to shore. And then, you know, fly back home, send the gliders back home. And again, we get access to the data and I mean, we did what I would say, a quick look analysis of the data. Most of the detailed analysis was done by actual marine mammal scientists, which makes good sense. But this was a real fun project and very rewarding. It's always interesting and to work on something where, you know, how the nature's awe is, you know, it's just so striking what these animals can do that it made it a very fun project. So with that, I think that's the last one. I want to again thank Jim Smith for making this opportunity available for me, and Professor Sun and everybody else, Leslie and Chris, within the name department. It's been my pleasure to well, present this. I hope folks found it useful, and if they have any questions, I'd say start with Jim Smith because he knows more than he's going to let on, and ask him. But if he doesn't know, he'll reach out to me, and between the two of us, we'll make sure you get, you know, we'll give you the answer if we can. So with that, I say thank you.
Jim, can you see the chat?
No, not right now, but it probably just means I haven't figured out how to use, hold on a second.
You should be able to click on yours at the bottom if you hover over it.
Remember, Jim, I'm on a Linux system.
Because you're sharing the screen, Jim, you should be able to go to the top along where it has, it should say your name that you're sharing the screen. If you click, there should be like a little down arrow that should give you more options. Within that, you should be able to see chat.
Oh,
or you can always choose to stop sharing and then you'll go back to the main Zoom window.
At this point, just so I don't waste people's time, why don't I stop sharing? And okay, now there's the main. Okay, now I see a bunch of other options. Oh, I see chat, and I see there's a couple.
So there's a question from Marika.
Oh, okay. So how much evidence of the beaked whales did you find? How prevalent were they where you searched? You know, that, as I mentioned at the end there, our job was really to build the collection platform for the data. So we didn't spend a lot of time processing the data. And there was a lot of data over, you know, if you think about recording at 250,000 samples per second for entire months and multiple missions. So the data sets were handed off to other folks to look at. In particular, there was a group at Oregon State, Dr. Holger Klink and Dave, I can't remember his last name right now, but anyway, they were responsible for the analysis of the data. I think it's fair to say that on pretty much every one of these missions, we detected beaked whales. I think if you were to actually Google, you know, if you put in some terms like sea glider, marine mammal surveys, and you know, you would come up with publicly available reports, I'm pretty sure, that would give you probably the kind of data that you're asking about and that I can't really answer.
Thank you.
You bet. Anybody else, or shall we call it good?
I think that's, yeah, and you know, most of the students, or you know, our interns anyway, you know, they know where I am down at the MHL, and you know, I think I've seen from some of the past speakers where Lisa has, you know, if people have further questions, you know, can get in touch with me, and then Lisa's able to kind of disperse, you know, further information. So. And there isn't there at APL, Kate Stafford, she's a marine mammal expert. Would she have anything available on like the beaked whales, or was that more Oregon?
No, Kate is, she studies low frequency whales or low acoustic frequency. So she wasn't really involved in this. It's really Oregon State and Holger Klink, K-L-I-N-C-K, I believe, has since moved to Cornell. But you could, if you looked up Holger, H-O-L-G-A-R, I think, he's a German, Holger Klink. He kind of led, and Dave Mellinger, that's the name I couldn't remember a moment ago. Those two guys kind of led the effort to analyze, especially with Holger running it. So again, I'm pretty sure that there are reports from their analysis that are available online. So poke around a little bit. If need be, I can reach out to those guys and possibly get a link. And I know that, Jim, I sent you a PDF copy of this presentation, and Leslie and Chris have PDF as well. So if folks want a copy, I would suggest sharing the PDF with them. The PowerPoint, which I've been using today, is rather large, like 55 megabytes. So it's a real pain to share, but the PDF is only 3 megabytes, so it's pretty, you can email it easily. And so there.
Cool. Well, Leslie or Lisa, is there a certain way to kind of send off, or?
Well, I just personally want to thank you, Jim, for being so available for us and for sharing all your knowledge and your experiences, and just thank you for getting up so early to be with us as well.
Oh, it's not really. I'm usually up at 6 o'clock anyway, so this didn't start till 9:45. So maybe it was time for my afternoon nap almost.
Oh, the luxury of retirement, right?
Indeed, yeah.
But thank you
This
so
has been
much.
this has been real fun. This is the first time I've ever done a presentation over Zoom, so I hope it was okay for the audience. Yeah.
It was perfect.
It was great, Jim. Thank you.
Thank you
Okay.
so much.
Well, with that,
right.
I wish everybody a good weekend, and stay safe from COVID and all that good stuff, and take care.
Thank you, Jim.
You
Okay,
too.
bye-bye.
Thanks, Jim.
You.